Thank you very much. And yes, as most of you have probably noticed on the program, Jay Boisseau was slated to speak in this spot, but due to some last-minute developments, he asked me to just step in the last couple of days. Unfortunately, not so close to the end that he'd actually prepared a talk. So I took his title, and we'll go from there. But yeah, it's really exciting for me to be here at this meeting, particularly given the theme this year of the TAMEST conference in computational modeling, because we at TAC, at the Texas Advanced Computing Center, are really a provider of the computational power and the designer and builder of the systems that enable all of these. So many of these talks we've heard today are from our users, and they make the premise of what I usually start out with. And as I said, as every talk is known, simulation is, obviously at this point, sort of ubiquitously critical across fields of science and engineering, and as I'm sure Tom talked about this morning, also really important to competitiveness. And I think in this audience, there's no reason to belabor this point, but I do want to point out that it's no longer simply about simulation, and I suspect Omar has spoken about this, but with the sensors and sequencers and networks we have, has created not only an explosion of data, but also an explosion of hype around what is called the big data phenomenon, which if I hear from another program officer, I'm going to have trouble dealing with in the near future. But the data there is real, even if the hype is perhaps somewhat overblown, as is the need to manage it, and it's really enabling some new modes of science, which is forcing us to change the way that many of our systems actually operate, and that we design them to sort of accommodate some of these. And of course, life sciences has really been the growth area in high-performance computing over the last several years. I don't really want to talk through the omics thing, because it's been talked through so many times, of the explosion of data in genomics and proteomics. I do encourage those people who think that there's a lot of data in genomics to look at astronomy, where we're into the exabytes at this point. But all that data is also real, and it's sort of the tip of the iceberg of life sciences data. And the long forecast $1,000 genome, of course, was announced this weekend, at least for the sequencing part. It turns out processing that $1,000 of sequencing still costs about $40,000 on Amazon to run the processor, or a lot less if you were to do it with us. But there will be the occasional plug. I do have a center. Imaging, a lot of the phenotyping techniques are going to produce far more data, vastly more data than I think the genomics and proteomics and transcriptomics will combined. And that's before you even get into categories like the electronic medical records. So it's really exciting for us that all these fields, some of the data things bring in social sciences, we have medicine, they're all coming to high-performance computing. We've been saying for decades we'd love to have them in high-performance computing, and we've had systems that look approximately the same but getting bigger and bigger, and programming models that have worked very well to support all these modes of science moving forward. Until now that you're all here. So now that all fields of science are starting to recognize the importance of modeling and the importance of data analysis, and that computation really does play an absolutely key role, is the time when we have decided to teach programming in probably precisely the wrong way for what's coming in large-scale systems today. And so if you look across labs, and as mentioned in the introduction, I run a very large project in bioinformatics in the plant science space, looking at crops and crop development. And we've interfaced with hundreds of labs and thousands of users. And I have joked that bioinformatics is often a synonym for knows how to use Perl. The standard practice is to use very high-level programming abstractions, to use scripting languages, and not just in the life sciences, but in general, if you just look at undergraduate curriculums across engineering, across the physical sciences, you see a lot of MATLAB, a lot of very high-level single-threaded programming, which was very effective in 1994. All of these sort of programming techniques are further abstracting the complexity of the systems that we're building today, the systems we've been building for the last couple of years, and certainly the systems we're going to build. And the hardware is getting more and more and more complex. So you might say, well, why don't you just build systems that the programmers can program? And there's a few reasons, and unfortunately none of them are within our control. So part of it is just simply the economics. In conventional computing, programmers are expensive and hardware is cheap, right? If you need 6 months of programming, to make your application go twice as fast, or you can just buy your postdoc a new $2,000 laptop. You're just going to buy the laptop. It's substantially cheaper. When your computer costs $150 million, that ratio is very, very different. So we're riding a curve where the hardware is designed around the notion that programmers are expensive and hardware is cheap, in a part of the industry where hardware is expensive and programmers are cheap. Because on a $150 million system, amortized over a 3-year lifespan before it's retired, so, call it tens of thousands of dollars per day, having your programmer work 6 more months to double the performance is well worth it. And the other trend that we absolutely have no control over that I want to talk about a little bit today is as we push towards exascale performance. It's the next big milestone. We're in the petascale era. I'm sure there have been talks that have covered how many petaflops can be delivered to something. We've come off terascale trillions. We're in petascale quadrillions. The idea is to get to exascale around 2018. But the driving force in almost every aspect of computing around performance today is power. That's because most processors go into cell phones where battery life is your number one constraint. And this is actually an amazingly large problem for science and engineering today. If you just look at any desktop or laptop machine that you can procure, they're all ENERGY STAR compliant. And there's a lot of tricks to make sure the processor never runs at full speed to keep them ENERGY STAR compliant. And you as a programmer on the other end have to know these tricks. So it's a heck of a lot easier to get a big, hefty 3.5 gigahertz laptop in 2005 and run fast science on it, particularly if you're running single-threaded MATLAB or Python code, than it is to get a modern, probably 2 gigahertz laptop with 7 times the battery life and get anywhere near the performance on that same code that you got in 2005. So we're sort of running in reverse on that trend. So as we try and get to exascale, there's actually a few, and I'm not really going to delve into these in great depth, but there's a few things we call the walls, the exascale walls, and I really just want to dwell on the power one, but there's about a half a dozen big challenges. And just to sort of summarize, because they do affect the architectures, there's the memory wall, which pretty much just states, as I put it on the slide, processors get faster than memories get faster. So we have this steadily growing imbalance between different parts of the system. And we can compute things faster and faster, but we can't necessarily get data in to compute on, which in an age when everyone is talking about big data, that's probably the wrong place to have an imbalance in your system. So the result of that is we're going to see more and more complex memory structures and I/O structures where we store data. It used to be processor, cache, memory, maybe disk. Now it's processor, register, L1 cache, L2 cache, L3 cache, GDDR, DDR, solid-state storage, spinning storage, nearline spinning storage, and offline storage. So 10 to 12 layers that you have to manage through your application, all of which have radically different performance characteristics. We have the error wall. Simply put, if you have a lot of stuff, it fails more. It's a technical concept. You just consider that if you can make a hard drive that can go, typical laptop hard drive, right? You might not have a crash of your drive for, say, 1,000 days, a little over 3 years. At TAC today, we have 12,000 hard drives spinning. If you do the math on one failure every 1,000 days on average, 12,000 drives, you get some insight into one of the dimensions that makes my life really unpleasant. There's the constantly forecast, since at least 1996, fact that we're 2 years away from the end of Moore's Law, right? That the transistor doubling is going to stop. That sky is not currently falling. It's always 2 years away. And I feel very confident about the next 10 years in that trend in the next 5 generations. So nothing to really worry about there, but that's always out there. And then finally, there's this power problem. And it really comes down to the fact that the relationship in transistors between the clock frequency, the rate that you switch those transistors, and the amount of power you consume has a factor of 3 on the wrong side of that fraction. So 10% clock frequency, 30% power increase, which is why you see things going from a clock frequency perspective slower and slower. So the solution in that situation, and the one that we're embracing largely, and the one that affects how all of these science problems have to execute in the near future, has been and really continues to be parallelism, right? Making copies of the same thing is how we've gone faster for a very, very long time. But increasingly at the chip level, we've gone from single core to dual core to quad core to 8 core. You see the trend there. So we're going to go lower frequency and use all those transistors that Moore's law gives us to get more parallelism, more scalability, and we're going to claim that we're still on the Moore's law curve, doubling not only transistor density, which is what Moore's law actually says, but performance, which is what people sort of interpret it to mean. So that can sort of manifest itself in 3 different ways in the chips that we're building systems out of. Usually it means more copies of the processor on the same chip, right? And that's the multi-core factor. And we're using some chips today that have more than 60 processors in them. That number is going to keep going up. It can also mean long vectors within the processor, right? So instead of saying I'm going to add A to B, I'm going to add 8 values of A to 8 values of B and do it as fast as I can do one of them and sort of replicate within the processor very simpler parts of the hardware. Or we can specialize the hardware to get hardware not just designed to do adds, but to do Fourier transforms or to do more complex operations directly in hardware and get performance there and use all those transistors for that. And all of the different things that undoubtedly vendors come and try and sell you when they offer you the new and faster computer, whether it's GPUs, graphics processors, the Xeon Phi, of the mini-core thing, field programmable gate arrays. All of these are variations on one of these themes, or usually multiple themes, right? We're going to make copies, we're going to extend the parallelism within a copy, and we're going to specialize the hardware in various places. And so those are sort of the 3 big ways we do that. As a result, if you take a look at the machines used to win the Gordon Bell Prize, so this is sort of the prize given to the highest performing real computation, not the machine, but the computation that's provided in the world every year. And we actually, I think, have several winners of this award in the room today over the years. But in 1988, the first time somebody hit a gigaflop, 1 billion instructions per second, that machine had 8 processors in it. So if you could write a program, and you could take your application and probably write the 8 different things it was going to do, you could get good performance out of it. In 1998, when we hit 1 trillion operations per second, faster processors, Moore's law, but there's also an increase in the number of processors. We used 1,024, and by the petaflop era started in 2008, 10 years later, hence our goal for 2018, we were at about 150,000 processors, and that's sort of on track to hit 1 billion. And it's not just in the very largest systems that are winning the Gordon Bell Prize. If you look at sort of the aggregate or the average rather, of the top 20 systems in the world from the top 500 supercomputers list, you see that we were on a trend of clock rate, clock rate, clock rate. Thank you, physicists, for getting us all that clock rate moving out. And then we went to core count, core count, core count more recently. And so I just pulled this chart off the shelf. It ends at 2009, but this exponential trend has continued, that even at TAC here in Austin, we have 5 times as many processors as this average from 2009 in our biggest system. So the growth rate continues to be more or less astronomical in this area. So what this means about hardware and software going forward and how we're going to have to build not just our machines, but our applications around them. If you think about the hardware, we're going to have staggering amounts of parallelism going forward, right? 1 billion threads is realistic. I gave talks for 10 or 15 years where I said, really seriously, the 1 million thread application is coming. It's not 10 or 100, it's 1 million. The machine we have today at TAC, to get full performance on it, you need 1.6 million separate little threads of execution, different independent parts of your program and running to get that sort of performance. So it's now not only coming, it's here. We're past 1 million, and it's going to keep going higher at an exponential rate. We're going to have these complicated deep hierarchies of memory. We're going to start stacking memory elements physically on the package, literally on top of the processor, inside the package, in silicon, and connect them together to get latency down. And then we're going to manage from that to off-chip, and that hierarchy is just going to get deeper and deeper. And again, the on-chip is going to be 100 times faster than the off-chip, and you're going to have to manage that in the software that runs all these computational models. We're going to have failures all over the place. The component count keeps going up, and we're going to have all kinds of fault-tolerant and recovery support built into the software. Do you think your grad student's Python code is going to work well on this machine moving forward, or your postdocs? I can give you a hint. No. There's a real chance, and I'm just going to round it off to 100%, that your problem, whatever your problem happens to be, I feel very good about this. If you're running on a supercomputer today, you're probably not going to get peak performance, as no one does. The contrived benchmarks that we use to solve big linear algebra systems will get about 90%. But you're probably not even going to get, unless you're among the truly elite of the computational tuners and performers, some of which are here, might get 40 or 50% on real applications. But there's a lot that aren't not only getting not 40%, but not 0.001%. And we've had two examples in the last couple of years that have really pointed this out that I pulled from life sciences in our crops project, but one from just a few months ago is a statistical method called PCIT. It's a partial correlation method. We're using it to do network inference, to infer function of genes within big regulatory networks. We did about 3 weeks of rewrite, and by rewrite I mean we took the code that they were using, figured out how it worked, tossed the whole thing out, and rewrote it in a different language from the ground up, and we got a 2600 speed up on the same machine, right? That was before we actually applied a supercomputer to it, but the difference was 2600, so that's just code inefficiency. Right? So whether you can buy a new computer that's 40% faster hardly matters if you have a factor of 2600 in code inefficiency in there. And that's the small one. We had one the beginning of last year, or actually the year before, doing single nucleotide polymorphisms, single SNPs. We were looking at pairs of SNPs and a big table of molecular phenotypes, essentially express behaviors, and trying to find every possible pair of locations in the genome that could be associated with a particular function. Which is a pretty simple algorithmic challenge. You're just doing some lookups between two things, but it was written in Python in the first cut, and we rewrote it in Fortran, and took about 6 weeks, most of it to figure out exactly what they were doing and to get the math written down. We got a speed up of 3 million on 128 processors. So at most you're getting 100 out of the hardware. The rest is Python sucks. But anyway, but high-level languages are the antithesis of performance today, and it's just sort of a massive challenge. So as a result of that, lately there have been a proliferation of papers in computer science journals and pretty much anywhere else where you can publish a faster algorithm that says if you just buy my GPU or whatever the product is, or I bought a GPU and I'm running it in my lab, and I can make your code go twice as fast. And I can assure you that, with a few notable exceptions, almost all of those millions of papers are wrong. Because all of them involve taking a code and rewriting it to make it fit on this new architecture. And at that point, you're comparing software implementations, and you're not really comparing anything about the hardware, because in the examples I just showed you, we can get a factor of 2600 rewriting the code on the same chip. So 30 or 40% should not impress you in any particular place. And so it just turns out, it's a very simple rule, that if you have a code written by someone whose goal is to write fast code and doesn't even look at the answer but the performance code, it's usually going to go faster than a code written by someone who just says, oh God, if I can just get this answer, I will get my Ph.D. One has a little more motivation to get the performance right. So the hardware performance is almost incidental, right? The signal-to-noise ratio is such that the signal is way below the noise in most of those papers. If we had a way that we could take unchanged codes and move them across platforms, things would improve. But the way that hardware is going with this pace of change and all the new kinds of specialization, it's going to fight us every step of the way. So that's sort of my call to do programming better. But fortunately, we do have some teams that do programming better and can take advantage of all of these new machines at nearly their peak performance. So let me also say that this is actually a really exciting time for supercomputing and a really exciting time to be at a place like TAC. The last sort of golden age of supercomputing was right before the end of the Cold War in the 80s. And that was because whatever idea you had for building a faster computer, you just go to the NSA and get $200 million for it. And they'd buy the first one for $200 million, no matter how much it cost to build, and then you'd sell them a few more. So, and as soon as that stopped, something like 35 supercomputing companies went out of business in 9 months. But we're back because we've hit this limit of what we can do in the conventional processor and the conventional clock rate, and it's opened up the architecture space again. And so I think it's a new golden age of processor design. We have the graphics processors, we have the folks doing ARM with single watt cores, we have the Intel Xeon Phi as the mini core approach that we use, 60 cores per chip, we have field programmable gate arrays, we have the IBM Power architecture, and we have the same sort of things going on, again, because of similar both market and technical trends that are running the current technologies out of gas. We have lots of exciting new things in network, most of which aren't announced yet, memory and storage devices, where all of these things are changing, and they just have to be adopted. You look at the rise of flash memory as a huge one in the last few years. One point I'd like to make is a huge number of these innovations happen here in Texas. We like to say Austin is the supercomputing capital of the world, not strictly because of TAC, but there are many small companies around Texas that are pioneering some of these new ideas here. Convey is sort of the leader in field programmable gate array-based supercomputers at the moment. There's many of the ARM companies, et cetera. All of the big chip companies have parts of their design teams here, whether we're talking AMD or IBM or Intel or NVIDIA. They're all based here. And then the big integrators are based, either based here in Texas or have huge presences here in Texas. So we really do feel like we have sort of the center of the supercomputing world, and we feel like we have the best academic HPC center in Texas here as well. We're just not good at the modesty part. So we've sort of embraced these technology trends I'm talking about across our systems. Both the ones we did last year, Stampede, the big one that has made a lot of noise, that I'll talk a little bit more about, in Maverick and Rodeo are the systems that we're currently, this is sort of the middle year for us between big deployments, but we're building systems that have very different capabilities than just crunching numbers in the way that we traditionally do. Maverick is for interactive and remote visualization. Stampede generates about 3 to 4 petabytes of data every month. So that's 3,000 or 4,000 terabytes. I think it's actually roughly the equivalent of all the genome sequencer output in the world right now. That's just what we generate from simulation on a monthly basis on the machine routinely. We do not have a network out of our data center that can move 3 or 4 petabytes a month. In fact, it takes about 3 months per petabyte to move the data out. So the solution there is, of course, you never move the data out. In fact, don't keep most of it. You move the answers out, which is a lot smaller than the raw data. So Maverick is our machine to do analytics on your data generated there without ever moving it. We're experimenting with less of a sort of utilization-based model and more of an interactive model with that. As the sort of software stacks, and I didn't get even into the cloud world, also diversify, we're building a system called Rodeo, which allows you to self-service Amazon-style your own software images and sort of diversify the software stacks. Stampede, as I mentioned, was where we first embraced this sort of mini-core approach. So almost 500,000 processors in that machine. I'm using the Xeon Phi, and again, more than 60 per chip in every one of that machine. So the idea of single-threaded code is just gone in this level of system. And then this year's deployment, which will be available at this time next year, almost exactly, the second week in January of 2015, will be Wrangler, which is our first purpose-built machine with this focused on big data. And I'll talk just a little bit more about that. So, am I right? One? Okay. Yep, so let me just say a couple things about the machines and close. As you may have heard about Stampede last year. As I mentioned, this is our 500,000 core machine. It's physically a pretty big machine. Its utilities are much bigger. And I never knew, getting a Ph.D. in computing, just how much I would know about air conditioning. And how to produce 180,000 gallons of chilled water an hour, which is what it takes to support this system. And that's back to that sort of power notion. This is just a side-by-side comparison of Ranger, 4th fastest machine in the world in 2008, half a petaflop, 3 megawatts. Stampede, much more power efficient, 20 times the computing capacity of Ranger at only twice the power. So 10x in power efficiency, still twice the power. That's about $3 million a year of electricity to run the thing. So you see where our big scaling problem is we can't afford to turn them on. And as again I mentioned, it is based on the Xeon Phi, this notion of many cores and long vectors, so 61 cores. That's just an image of the chip itself. And Wrangler, as I mentioned, is the next one up. I can't say too much about it, but it is part of this new and innovative culture of startups around here. what is out is we've sort of partnered with the folks who originally founded Sun Microsystems on a new flash technology for this. And really the special thing about it will not be that it will process faster than Stampede, but we're solving this problem of not being able to get the data to the chips fast enough. And so we'll have an all-flash-based memory subsystem where we can do a terabyte a second. That $1,000 genome machine that was announced this weekend does about a terabyte a day. So what it can produce in a day, we can process in a second at this point, and we can do it at random access. So the current world record, not that there's a real good measurement of record, it's about 30 million I/O operations per second. We'll do 250 million, so 10x what is currently the best in the world in this. But what that means at the individual model level, for those of you running models, is we'll be able to move 400 times as much data per processor through this machine as we could on Stampede if you maxed out the file systems. So I think it's really going to change the way we approach some of these streaming data-based models. So, and of course, all of these systems that I mentioned do lots of science every day. Many of our users are here, but 3,400 scientists and over 2 million jobs on Stampede last year. And you don't give these talks long if you don't put your NSF award number up every time you do it. So let me just close with this great graphic that our team put together that might be a little too small to read, but it's on our website today, tac.utexastudy.edu. About January 7th was the first year Stampede had been in production. And 1,247 different projects, so it's different PIs with different grant awards, have made use of the system in the first year. And you can see the breakdowns of science and everything else. So, but you know, my takeaway message here is it's not just a tool where we turn the crank and build a faster one every year. We really have to work together with the modeling community and our colleagues to continue to build models that can use these systems as they get more complicated, but they're going to keep getting exciting and keep getting faster. So thanks very much. And I think we're only 5 minutes past the end of the break, so I did okay. So, yeah.
I'll phrase the question in a somewhat provocative way. Would it be to the benefit of innovation in the industrial sector in this country if we cut the if we cut the Exascale Initiative budget in half and gave the money freed up to fund development of significantly new programming models for high-performance computing?
So that's an interesting question in a lot of ways. And so the Exascale Initiative, and Exascale is the short form. The long form is build a machine that is in general useful to the community, that has more than an exaflop of peak performance, and also costs less than $200 million by 2018. Because we could build an exaflop tomorrow. I'd like $2 billion, please, but promise I could do it. So, so first of all, a couple of the political dimensions of that. One is the Exascale budget's already been cut in half, and I'm not sure the rest of it's actually committed at this point. So they have the 100 petaflop budget in hand, and that's as far as it goes at the moment. So were it funded, then you could talk reallocation, and there actually is a significant piece of it dedicated to programming model. In fact, the original, I also forgot part of that sentence. To build a machine generally useful over an exaflop under $200 million deployed by the Department of Energy. So that's where the budget is. And there is a part of the DOE funding in the concept they had of co-design, which is as we get this level of complexity, let's design the software models and the applications along with it. But I do feel like that's an underfunded piece of the initiative, even if it were funded at the planned level. You know, in my experience, the applications that use the full system are critical, but are not most of them. There are certainly drivers that take advantage of that technology and use just a fraction of the system, but they need to be programmed in the same way. If the question is, am I in favor of more funding for developing advanced programming models, heck yeah, is my answer. Can the Exascale budget get any lower and still deliver Exascale? It's probably already below that threshold. So that's an interesting question.
I guess you know, there are certainly national security applications, but I think probably a lot of the science that we're hearing about in this conference is being conducted by groups that are not equipped to do the kind of tuning and optimization for highly parallel architectures that we're now focused on developing?
So I think that is probably true, although there are a number here who are our top users in that. Omar's still around. He would be in that category. But part of it is that almost no attention is paid to those optimization and tuning things. And part of mini-core at the chip level means these optimization techniques we need at the large scale, we're also going to need at the node level because they're going to have mini-cores and the deep memory hierarchies. So where I think the attention needs to be paid is in changing the way we're teaching programming to pay attention to some of these things, because they're not, they are somewhat complicated, but they're not necessarily PhD level complicated, right? A course or two could fix many of these things, and the development of the tools which need funding. So I absolutely think we need further investment in those kinds of things.
Thank you.
This is actually a follow-on to that same line of questioning. What do you see coming in the way of, and I recognize your disdain for interpretive languages, by the way, but they're everywhere, Mathematica and so on.
Absolutely.
What do you see in the way of autocode technologies or programming aids to map from interpretive languages to make the first step to good C or good Fortran that would be suitable for massive parallel computation? Do you see anything making a move in that direction?
Yeah, it's also really a fascinating question in a lot of dimensions. So, sort of the automatic extraction of parallelism and autocode generation has been the holy grail of parallel programming since the 1960s at least. So there's some tendency to sort of just discard it at this point. But I think it's a poor tendency because there's been really huge strides in sort of these auto-tuning libraries in particular in the last few years and applying some machine learning techniques and various optimization techniques to that. And I think where the interpretive languages, because they are ubiquitous, right, and they are going to play a role, the way we're going to solve that is by building libraries that can tune for architectures and embedding them under those languages, right? Because it's not that every single line of code necessarily has to be optimized. It's that the key functions that you use in MATLAB need to rely on a C or a Fortran library that tunes itself and is performant on modern and large systems. And honestly, I think understanding, and particularly, and there's actually a small effort led by Rick Stevens at Argonne to look at this, but in the disciplines that are emerging in HPC, right? If you run linear algebra problems, we've got you covered. Right? We've been working on that for decades. There are many great libraries. The Intel math kernel libraries at this point do a phenomenal job of taking advantage of the power of a processor. You can hide them under MATLAB, and away you go. But we don't have that same sort of core set of primitives around genomics or around graph mining. And I think if we can, and so the genomics effort is the one Rick Stevens is leading, is what are the core operations that we could build a few really good tuned C and Fortran libraries for, and then put them under the interpretive languages to take advantage of them. And I think there's a bright future in that, and it's another area, it's an area ISIS at UT Austin has invested in, is libraries that can embed the performance, also understand uncertainty, some of the things we want to do with libraries that they've invested in. And I think that area has a lot of promise, but it is also sort of not paid attention to. What directorate does that sit in at NSF is the real question there.
We have seen that the number of operations per unit time is growing exponentially with time.
Yep.
What about the cost per operation? Is that decreasing exponentially with time?
Not exponentially. So the cost is decreasing over time pretty dramatically, and the power efficiency, the power per operation is also decreasing. But our growth in performance is faster than Moore's law, right? It's 10x, 1,000x every 10 years. Is sort of what we're getting in aggregate performance. Our cost factor, more or less, is following the Moore's law curve, right? So every 18 months to 2 years, the great part of Moore's law is you can plug in your own constant, just doubles in some time period, so that's really handy. But every 18 months to 2 years, it costs about half as much to get an operation, and your power efficiency is improving about 10 or 15% in that same time. So hence, Stampede and Ranger cost the same amount. Actually, Stampede was slightly less in cost. It's 20 times the computation, but still twice the power in the same sort of footprint. So, so costs are scaling relatively fast. And in fact, That's why I put that caveat on Exascale, is the fastest machine in the world is not the fastest machine we can build. It's the fastest any country can build for under $200 million. Is really what it amounts to. So that's really what we're measuring, is the cost per operation. So that's sort of scaling with performance.
Thank you.
Hi. You had mentioned the power limitation,
Uh-huh.
and we saw with Stampede, we were on the order of megawatts here. In the early days of digital computing, people had looked at reversible gates, which would be vastly more efficient. Do you foresee in the future a move towards some role of reversible gates to replace the irreversible gates that we use now as a means of getting more efficiency?
Yeah, so the honest answer to that question is I don't know. I've read some of those papers about reversible logic, but I haven't seen. What I can say is, from what I know of vendor roadmaps going forward to the non-disclosure and super secret non-disclosure levels for the next 7 or 8 years, I don't see a lot of investment in that area. I'm not entirely sure why that is. At a guess, I would say, as we move to the 5 or 6 atom thick transistors in a few years, just anything that switches is success, and add an additional complexity is sort of not available. But I'm not really a circuit designer. I was at one point 20 years ago, but I'm not really a circuit designer full-time anymore, so I don't know why they haven't really embraced that. But I have seen that technology, and I just don't see it in the roadmap, so I don't know what's going to happen there. Mm-hmm.
It's a concept that's fundamental to quantum computing, for example, but that's a very different principle, and it'll be interesting to see if some of those ideas filter back into the digital world.
Yes, very much so.
Thank you.